So number theory will just a number of concepts about addition, subtraction, multiplication, division, which you all know, but we'll adjust it a little bit from what you commonly think about. And then see a few equations which were useful, and some other properties of numbers which are useful when it comes to public key cryptography. We'll start very simple. We'll talk first about divisibility in prime numbers, and I think you learn even in primary school now that we can talk about one number divides another number. So we can say B divides A if there's some m, some integer m, such that when we multiply by B, we get A. Right? That is, if we can divide and there's no remainder, we say B divides A. And we talk about divisors. So we can say B is a divisor of A. If we can take A and divide by B with no remainder, we say B is a divisor of A. Sometimes we may write that in a short form of B vertical bar A. So we know about divisors. We can then also, given a number has a set of divisors, we can talk about the greatest common divisor amongst two numbers. So A has a set of divisors, B has a set of divisors. What's the greatest of that set? The greatest common divisor, or GCD. And there are algorithms for finding the greatest common divisor. We'll go through a couple of short examples. And a new thing that you may not have heard of, or you can't remember, if two integers, A and B, have a greatest common divisor of 1, we say those two integers are relatively prime. A couple of examples. What are the divisors of 16? Start simple. 2, is there a number before 2? 1, all right. We can divide by 2. We cannot divide by 3. Okay, so it's simply the divisors, easy. 24. We can divide by 3. 4 by 6, 3 by 8, 2 by 12, 1 by 24. So that's the divisors. Greatest common divisor of 16 and 24. Well, the greatest value there is 8. Okay, that's all. We've done this many times in high school, primary school maybe. 15 divisors. 1, 3, 5 and 15. Greatest common divisor of 16 and 15 is 1. If we look at those sets, 1. So we say there that 15 and 16 are relatively prime. They're not prime numbers. We'll see them later, but we say that those two numbers are relatively prime to each other. 15 is relatively prime to 16 and vice versa, because the greatest common divisor is 1. And another thing you probably know is that we can often write, well, that's all we've gone there. The next thing we know is about prime numbers. So instead of writing the divisors, we often think about the primes. So what are the primes on the slides? What's a prime number? Any integer greater than 1, if and only if its only divisors are plus or minus 1 and plus or minus p itself. It can be divided by 1 and itself only. And we can say any integer can be factored into the prime. So the divisors can be written as a set of primes multiplied together. So the divisors, we also say the factors of 15, 1, 3, 5 and 15. So we can talk about prime factors of a number. So some integer a can be written as multiplying a set of primes together, prime numbers only. Sometimes there'll be multiple primes multiplied together. So we can talk about the prime factors of a number. What are the prime factors of 16? How can we write 16 as multiplying primes together? And let's forget about 1. All right. So what's the first prime? 2. 2 is a prime. It can only be divided by 1 in itself. 1, our definition, we consider greater than 1. Okay. So 2. 2 to the power of 3. 2 to the power of 4, sorry. Right? 16 is 2 times 2 times 2 times 2. So its prime factors are 2, and so the factor is 2, but it's 4 times there. 24 is what? What are the prime factors of 24? 1's not. 6 is not prime. 2 and 3, 2 to the power of 3 is 8, times by 3 is 24. So 2 and 3 are the prime factors. But we can say 24 is... So in fact, what we can generally do, we can do it for 15 as well, if we want to. Three and 5 are the primes there. In general, any integer can be expressed as multiplying primes together, and sometimes we just list it in a general form, such as here. There's a mistake here. It's not P2, it should be P1 as the first subscript. That is, some integer is prime 1 to the power of some positive integer, 0, 1 or above, times the second prime. So prime 1 is 2, the second prime is 3, the third prime is 5, and so on. So we can multiply the primes and give some exponent, and that will create any integer. So we'll often come back to prime factors. Some number can be written as multiplying primes together, or the other way, given a number, we can find those factors. What are the prime factors of a number will come up as an important problem. What's the prime factors of 22? Two and 11. 145. There are 2 as a hint. 5 and 5 times what? 29. 5 and 29. So, all right, a little bit more work in the head, but we can find prime factors. And there are algorithms for doing so, and we'll come back to it, but an important point for security is that for a very large number, not 145, but maybe a number with 145 digits, a very large number, it takes a long time to find the 2 prime factors. That is, if we multiply 2 primes together to get a very large number, given that large number, it's hard to work out what the primes are. And that will be a feature of some of the encryption algorithms. What are the primes? You should start remembering some of them, not all of them, of course, but for the simple problems, you can remember the first 5 or 10. So there are lists of primes you can find. You'll quickly remember them. All right, easy. We can divide numbers. We know something about primes. Let's do some arithmetic. Some addition, subtraction, multiplication and division. Of those 4 operations, well, are there any other operations in arithmetic? Maybe we can expand exponentiation. All right, we add numbers, subtract, multiply, divide, raise to the power, exponentiation, a to the power of b, and the opposite of raising to the power, logarithm. Okay, the logarithm of a number is the opposite of exponentiation. So think of those 6 operations. And you know they're related, so they all go in pairs. Subtraction is really addition. Subtraction in our arithmetic is adding a negative number. All right, to subtract a number, we add the negative. The negative of a number, we will say, is the inverse, the additive inverse to be specific. We'll list that in a moment, but we'll introduce and say if we add the negative of a number, we get subtraction. So subtraction is just addition where we add the additive inverse of a number. And similar, multiplication and division go together. Division is just the inverse of multiplication. That is, to divide, we multiply by the inverse of the number. 10 divided by 3 is 10 times 1 divided by 3, 1 over 3, the inverse of 3. Right, so we can talk about multiplication, and division is just multiplication times by the multiplicative inverse. So we'll introduce that. And similar, their exponentiation and logarithms go together. And that will become important again when we look at cryptographic algorithms. So I know you can do all those 6 operations. Now we're going to do it mod n, modular arithmetic. And most of it's the same as your normal arithmetic, but we just mod by n at the end. Well, we know what mod n means. Well, sometimes it's not so clear. Do we have a positive or a negative number? So we'll say a mod n, a is an integer, n is a positive integer, is the remainder when a is divided by n. Okay. We refer to n as the modulus. We can say that 2 integers, a and b, we can think are equivalent. We call it congruent modulo n if those numbers mod n are the same. 12 mod 10, 2 mod 10, 22 mod 10 are all congruent modulo 10. They're all the same in mod 10. 2 mod 10 is 2, 12 mod 10 is 2, 22 mod 10 is 2. So we say they're congruent modulo n, and we'll try and write that as 3 lines in the equals. So we'll think of mod n as an operator. Some number, mod n. And it returns an answer in the set of 0 up to n minus 1. So mod 10, the answer was always between 0 and 9. No negative values, always positive, 0 to n minus 1. So we'll sometimes write that as the set Zn. When we perform modular arithmetic, we do addition, subtraction, multiplication, division, exponentiation, logarithms, where the answers are, or the operations are within the confines of that set Zn. So we'll go through some examples of those 6 operations, mod n. Start simple. Just yell out the answer so we can move along quickly. There's no need to follow the lecture notes, just some examples today. And to go through these examples, how about the 5 or 6 students at the back come down to the front so we can all hear clearly. Come down to the front seats. Let's turn off these 2 monitors. Plenty of spare seats down the front. Then I can hear you when you tell me the answer. We know 13 mod 10, the remainder is 3 when we divide by 10. 13 divided by 10, the remainder is 3. We can say 13 is congruent modulo 3. Congruent modulo 10, they are equivalent. In mod 10, 13 is the same as 3. In the set Z10, the answers go up from 0 to 9. So when we're doing mod 10, the answer is always between 0 and 9. So let's do some addition. And in these examples, we'll do everything in Z10. Everything's mod 10. I'm not going to write the mod 10. All right? So some examples. Addition. What's 4 plus 3? Easy. 4 plus 7. Not 11. 11 mod 10. All right, so everything's mod 10. So in addition, it's easy. We just do our normal addition and then mod the answer by 10. So 4 plus 7 is 1. So addition in modular arithmetic is very simple. It's natural for our perspective. We just mod the answer by our modulus n. Subtraction. Well, let's do subtraction in, over here I'll write the normal arithmetic. That is our no modulus, just normal arithmetic. In normal arithmetic, what's 7 minus 3? 4. Or 7 plus minus 3. Subtraction is just addition, where we add the negative number. So 7 minus 3 is really 7 plus minus 3, where minus 3, we say, in our normal arithmetic, minus 3 is the additive inverse of 3. The additive inverse of a number is the number we add to it such that we get 0. What's the additive inverse of 3? 3 plus minus 3 gives us 0, so the additive inverse of 3 is minus 3. This is our normal arithmetic. Additive inverse, since, and I'll write the sign as well, plus 3 add minus 3 equals 0. Therefore, just in brief, the additive inverse, AI, additive inverse of 3 is minus 3. The point being is that we don't need to do subtraction, we just do addition. Subtraction is addition plus the additive inverse. So we need to find the additive inverse to do subtraction. That's normal arithmetic. Let's return to Z10, everything mod 10. What's the additive inverse of 3? Write it down. Additive inverse of 3. This is in Z10. Z10 means the numbers, the answers between 0 and 9. So don't give me a negative answer. What's the additive inverse of 3? What number do we add to 3 such that we get 0? Same as here in the normal arithmetic. What number do we add to 3 such that we get 0? Negative 3. 3 plus 7 equals 0 in mod 10. 3 plus 7 is 10, mod 10. So yes, the additive inverse of 3 is 7. Because in mod 10, of course, I haven't written. 3 plus 7, mod 10 is 0. So we can talk about an additive inverse. If we can find the additive inverse, then we can do subtraction. Another one. What's 4 minus 7? Four minus 7 is 7. Okay. 4 minus 7 is 4 plus the additive inverse of 7. What's the additive inverse of 7? What number do you add to 7 to get 0? Well, actually, we just did that. 3, but it was the opposite. That is, the additive inverse of 3 is 7. 3 plus 7 equals 0. Therefore, 7 plus 3 also equals 0. So the additive inverse of 7 is 3. 4 minus 7 is 4 plus the additive inverse of 7. Subtraction is just addition, where we add the additive inverse. We know the additive inverse of 7 is 3. So it becomes 4 plus 3. And now we just have normal addition. Mod 10, 7. 4 minus 7 is 7. So in modular arithmetic, addition is natural to us. That's easy, I think, for most people. Subtraction is a little bit different from how we think. We need to find the additive inverse. But it's in fact the same principle of our normal arithmetic. Two minus 6. Find the answer. 2 plus the additive inverse of 6. 6 plus 4 equals 0. So it becomes 2 plus 4 equals 6. 5 minus 3. 5 plus the inverse of 3. We found that before. The additive inverse of 3 is 7, so it becomes 5 plus 7. Two. Remember, everything's mod 10. 5 minus 3 is 2. All right, that makes sense. 2 minus 6 is 6 in mod 10. Any questions so far? Yep. There are no negative numbers. All the set Z10, mod 10, means the answers are always between 0 and 9. So this is the difference between our modular arithmetic and our normal arithmetic. We define everything is within that set of 0 to 9. So there are no negative numbers. Back to the additive inverse. Let's consider all possible values in our set. We're in Z10. All possible values. A can be 0. They are the possible values that we can operate with Z10. What are their additive inverses? 0 plus what gives us 0? Mod 10. These are easy. All right, so in this case, every number in our set has an additive inverse, and in general, in any set, in any mod n, every number has an additive inverse. Doesn't matter it's Z10, Z8, Z1 million, that is, whatever the set, whatever the modulus, we'll always have an additive inverse of each number. Meaning we can always do subtraction, because subtraction is adding the additive inverse. Any questions before we move on to the next operations? Addition and subtraction, easy so far. What's next? What's the next operation? If we can add numbers, we can subtract numbers, we need to multiply numbers. Multiplying is what? Adding multiple times. So there's a relationship between multiplication and addition. So let's look at multiplication and then division. And let's do it in Z8, just to make it more fun. Three times 2. Are you sure? What's the answer? 6? Okay, good. Three times 4? 3 times 4 in Z8 is 4. Remember, everything's mod 8. Remember, everything, we're just omitting writing the modulus. And the same with 3 times 2 equals 6. Mod 8, we still get 6. Multiplication is easy in modular arithmetic. It extends upon addition. We just do naturally our normal multiplication mod by our modulus n. What's the next operation then? We can do multiplication. Next is division. What is division? Multiply by the inverse. Is that? In our normal arithmetic, 10 divided by 3 is 10 times 1 divided by 1 over 3, we can think, the inverse of 3. Not the additive inverse, but we say the multiplicative inverse. So we introduce the multiplicative inverse. Again, this is our normal arithmetic, what we know. Division, 8 divided by 3, in fact is the same as multiplication, 8 times 1 over 3. Right? So we can convert division to multiplication, where we say since 3 times 1 over 3 equals 1, therefore the multiplicative inverse of 3 is 1 over 3. This is our normal arithmetic, no modulus yet. The multiplicative inverse is defined as the number we multiply by such that we get 1. 3 times 1 over 3 gives us 1. So 3 and 1 over 3 are the multiplicative inverses of each other in our normal arithmetic. So division, divide by 3, is 8 times the multiplicative inverse of 3. 8 times 1/3. So that holds also in modular arithmetic. Back in Z8, 5 divided by 3. What do you get? Find 5 divided by 3 in Z8. Phone calculator may not have this answer. Okay, these are the ones you need to do in your head. 5 divided by 3, 5 times the multiplicative inverse of 3. Let's do the full steps. Division is multiplying by the multiplicative inverse. The multiplicative inverse is the number that we multiply by such that the answer is 1. What times 3 gives us 1? In mod 8. So 3 times 3 gives us 9, mod 8 gives us 1. So the answer is 3. The multiplicative inverse of 3 is itself. Because 3 times 3 equals 1. Therefore, 5 divided by 3, continuing, is 5 times the multiplicative inverse of 3, which is also 3, which is 7. 5 times 3, mod 8. Remember, we're all mod 8 at the end. For multiplication and addition, just do the mod 8 at the end. Easy to solve. 5 divided by 3 equals 7. Any questions before a couple more examples? So think about additive inverse, the number we add to get 0. Multiplicative inverse, the number we multiply by to get 1. Subtraction is adding the additive inverse. Division is multiplying by the multiplicative inverse. Yes. This. This is from our definition. We want to find the multiplicative inverse of 3. What does that mean? Similar to our normal arithmetic, it's the number that we multiply by that gives us 1 as the answer. Everything's mod 8, remember. Something times 3 equals 1 in mod 8. So something times 3 mod 8 equals 1. What is that something? It's actually 3. It's itself. 3 times 3 mod 8 gives us 1. So we say 3 is a multiplicative inverse of itself. Yes.
There are actually, because mod operation, there are more, this 3 is not unique when you apply inline.
What other answers are there?
Well, theoretically, it's not unique, or do we need to define the
so what? Right. The answers, remember, also always within the set Z8. So 3 times 3 is 1, mod 8. There's another answer which is, can I think of it? Something times 3 mod 8. Yes, there are numbers greater than 8 that will give the answer, and I can't think of one right now, but there are. But if those numbers are mod by 8, it will come back to 3. Right, so the answers or the numbers are always within the set Z8, 0 to 7 in this case. Three times 11 is 33, mod 8 is 1. Right, you found one. 11, 3 times 11. But what is 11? It's 3 in Z8. In mod 8, 11 and 3 are the same. They're congruent modulo. Okay. So, yes, 3, 11, probably 19, and so on, I think, when we mod by 8. The reason we're doing this is we're working our way up. Addition and subtraction are not so, we don't see them so often in cryptographic operations, but we've moved from addition and subtraction up to multiplication and division because they are based upon addition and subtraction. And then the next step is the exponentiation and logarithm, and we'll see that they are commonly used in cryptographic operations, public key cryptography. So that's why we need to learn about the principles here. Do you need to show the operations? Yes, sometimes there's a small question. Solve by hand one of these. But usually not such small ones like addition and multiplication. 6 divided by 4. Find 6 divided by 4. There are no fractions, there are no negative numbers. The answers are between 0 and 7. The integers between 0 and 7. How do you find the answer? Well, 6 times the multiplicative inverse of 4. So we need to find the multiplicative inverse of 4. Something times 4 mod 8, we'll write it down in full here, we're still in Z8, equals 1. Where that something is 0 to 7. No answer. There is no such number. Okay, so 4 does not have a multiplicative inverse. There's no number between 0 and 7 when we multiply by 4 and mod by 8 and get 1. So there is no answer. Not every number has a multiplicative inverse. Every number has an additive inverse, but not every number has a multiplicative inverse. 4 does not. So we cannot do that. There's no answer. There's no multiplicative inverse of 4. Staying in Z8, so let's list them. What are the multiplicative inverses of the 8 numbers? Zero times something equals 1. There's no such number. 1 times something equals 1. 9 is not in our set. Remember, our answer is 0 to 7, so 1 times 1. 1 is its own inverse. 2 times something equals 1. Well, we can't get an odd number when we multiply by an even number here, so no such answer. 3 we saw as itself. 4 we don't have an answer. 5 times 5, mod 8 is 1. 6 won't work when we mod 8. 7 times 7, mod 8 is also 1. In Z8 it turns out 1, 3, 5 and 7 are multiplicative inverses of themselves. But it's not always the case. Let's go back to Z10. To show another case. Zero cannot be multiplied by anything to get 1. This is mod 10. Now, 1 will always be a multiplicative inverse of itself. Doesn't matter what the modulus is. 2 won't work. 2 times something mod 10 gives us a remainder of 1. And even multiplied by something else will always give us an even number. We can't get a remainder of 1. So the even numbers are not going to work. 3 and 7. 3, 7, 21, mod 10 is 1. 5. No, there won't be a remainder of 1 when we mod by 10. 7. We've got that one. 9. 9 nines. 81. So just a different set of multiplicative inverses. In Z8 they were inverses of themselves, but that doesn't have to be the case. Right? As we see with Z10, 3 and 7 are multiplicative inverses. And another important point, not all numbers have a multiplicative inverse. So we can't divide by just any number, only by some. Which numbers do have a multiplicative inverse? When the remainder is 1, if the two numbers are relative, if the number is relatively prime with the modulus, it will have a multiplicative inverse. What's the greatest common divisor of 1 and 10? 1. 1 and 10, the greatest common divisor is 1. 3 and 10, greatest common divisor, is 1. 7 and 10, 1. 9 and 10, 1. 8 and 10, it's not 1. 6 and 10 is not 1. 5 and 10, it's not 1. That is, a number has multiplicative inverse in mod n if that number is relatively prime with n. Relatively prime means the greatest common divisor is 1. That is, we'll not list them all, but greatest common divisor of 1 and 10. We can list them all. 3 and 10. 7 and 10. They're all 1. That is, all those numbers are relatively prime with 10, and therefore they have a multiplicative inverse in mod 10. So when we want to do division, we need to know which numbers have an inverse, and we can find them to check if that, by checking if they're relatively prime with a modulus. We can do addition, subtraction, multiplication, division. We can't do division in all cases, only when we have a relatively prime number to the modulus. Let's come back to the slides, see what else we've said. The properties or the laws of our normal arithmetic, there are similar laws of modular arithmetic, and some of them are obvious. These three, for example, A plus B mod n is the same as A mod n plus B mod n, all mod n. And the third one is especially useful. A times B mod n, we can expand out, be A mod n times B mod n, and then all mod n. Remember, if you mod a number mod n multiple times, if you add A mod n is the same as A mod n. If you add another mod n at the end, it makes no difference. 12 mod 10 is 2. Mod 10 again is still 2. Mod 10 again, it's still 2. So we can add mod n's at the end, making no change to the answer. This third one is sometimes used to simplify multiplication. When we have large numbers, we can expand out. Two large numbers multiplied together gives us a very large number, then mod n. An easier way to solve that is to take those two large numbers a and b and mod n first, which makes them smaller numbers. Multiply two smaller numbers is easier, and then mod n. So that's a common way to, both in our heads, do calculations of multiplication, but also computers can use algorithms or laws like that to speed up the calculation. And there are other laws there. Let's see an example of this third rule. And then we'll move on to some other concepts. Staying in Z8. A simple case, we could probably do it in our head, but let's see if you can expand to solve it a little bit easier. 132 mod 8. Well, you could try and calculate what times 8, what's the remainder. But the property that we can take advantage of to make it a little bit easier, if we recognise anything about 132, what are the divisors of 132? Something times something is 132, maybe. If you know your times tables. There are some small numbers, but 12 times 11, There are other ways to do it. But 132 is 12 times 11. So we can expand that. Twelve mod 8 times 11 mod 8, all mod 8. 12 mod 8 is 4. 11 mod 8 is 3. 12 mod 8, 4. Okay, that's just an example of doing this expansion to maybe make it a little bit simpler. Right? Now these numbers you could do it either way in your head. But as the numbers gets larger, especially even for computers, it makes it easier if you expand because these numbers become smaller before we multiply. Try that one. A couple of minutes. Try to expand and do it without a calculator. No calculator. Solve that. 11 to the power of 7 mod 13. And try and use the expansion to solve it. Just to see how powerful it is. Good. So one approach to this is think, right, let's make this number smaller. (11 to the power of 7 is 11 to the power of 4 times 11 to the power of 3. Or, even better, no, let's stick with that. (11 to the power of 3, I'm not so good at my multiplication, so even that's too big for me. Maybe we can split that up. We'll come across here. I know my squares. I know 11 squared, but I don't know 11 to the power of 3, so we can think of that as 11 to the power of 4 is 11 squared squared mod 13. Times 11 to the power of 3, I don't know, but I know that's 11 squared mod 13 times 11 mod 13, 11 to the power of 1. And let's not forget a mod 13 at the end. Some of these numbers I can do in my head now. (11 squared, 121, mod 13. Can someone do that for me? 4. 11 mod 13. (11 squared mod 13). 11 squared is mod 13 is 4, and then square that again is 16 mod 11. Let's leave it in here. just to be complete. 4, 11 squared mod 13 gives us 4 squared mod 13. (16 mod 13), we get 3 times 4 times 11. We could probably do that in our head. 12 times 11, actually that was before, 132 mod 13. Divide by 13, the remainder is going to be 2. (10 times 13 is 130. Right? The idea of this is that this expansion makes large calculations much simpler. Not just for you in a quiz or an exam, but for a computer that has to deal with very large numbers. Very large numbers may be hundreds of digits. Not hundreds, but hundreds of zeros of numbers is the length of the number. Multiply them together, calculate the modulus, takes time. So break them into smaller numbers. What's next? That was an example of this property that we could use. And that's the main one we'll see in the cryptographic algorithms. Division we've talked about. We've defined additive inverse, multiplicative inverse. Some number has a multiplicative inverse in n if it is relatively prime to n. So we can do division. In the last 10 minutes, before we won't introduce the theorems, we'll do that next week, let's consider another thing, relatively prime. How many numbers are relatively prime to 10? Back to our examples. How many numbers are relatively prime with 8? One, 2, 3, and 4. All right, how many? Just counting them. How many numbers were relatively prime with 10? 1, 2, 3, and 4. 4. It's not always 4, but let's consider counting the number of numbers relatively prime with some number. Let's get a different colour. Start simple. For example, how many numbers are relatively prime with 4? And less than 4. All right, we'd need to test 3 numbers, 1, 2, and 3. Are 1 and 4 relatively prime? 2 and 4, 3 and 4. So relatively prime, remember, means the greatest common divisor of 4 and 1, 4 and 2, so we'd like to count how many numbers less than 4 are relatively prime with it. 4 and 1, greatest common divisor is 1. 4 and 2, divisor is 2. 4 and 3, divisor is 1. These are relatively prime. This one's not. So two numbers less than 4 are relatively prime with 4. The count of numbers. And we have a special name for this. The number of numbers less than n which are relatively prime with n is called Euler's totient. Euler's totient function, spelt E-U-L-E-R-S, the top part here. Euler's totient function, written so the totient, we say, easier to say, the totient of n is the number of numbers less than n which are relatively prime with n. The totient of 4 equals 2. We did it before. The totient of 8, we had, from our previous example, we had 4. The totient of 10, from our previous example, we counted 4 numbers. What's the totient of 9? Euler's totient function is defined as the count of numbers relatively prime with n and less with n. So the totient of 9, consider the numbers from 1 to 8, check if they're relatively prime with 9, and count how many are. Well, let's... One and 9? Are 1 and 9 relatively prime? Yes, 1 in any number is always relatively prime. 2 and 9? Greatest common divisor of 2 and 9 is 1. So yes, they are relatively prime. 3 and 9? Greatest common divisor of 3 and 9 is 3. So no. 4 and 9? Greatest common divisor is 1, so yes, I'll give it a tick, it is relatively prime. 5 and 9. 6 has a divisor of 3, so does 9, so no. 7's okay, 7 and 9. And 8 is also okay. 1, 2, 3, 4, 5, 6 numbers. Euler's totient of 9 is 6. All right, just to make sure you know what you're doing, let's try another number. We'll not write it down. 1 and 13, yes, 1 and n always relatively prime. 2 and 13, think of the greatest common divisor. Greatest common divisor between 13 and 2. Is it 1? If so, relatively prime. 2 and 13 are relatively prime. How many numbers less than 13 are relatively prime with it? All of them. 12. Okay? Because of what? 13 is a prime number. By definition, then all of the numbers must have a greatest common divisor with that number, that prime number of 1. So the numbers less than 13, which are relatively prime with 13, 1 through to 12. So there are 12 numbers. So that's a nice shortcut. The Euler's totient of a prime number is the prime number minus 1. If you recognize 29, it's a prime number. Totient is 28. So if we know n is a prime number, we can quickly calculate the totient. Very easy. If it's not a prime number, then, well, we saw the algorithm on our small numbers. We could check the numbers. Right? We go through and check them. If it's a prime number, we don't have to check them. We know straight away that if 29 is prime, the answer of Euler's totient of 29 is 28. But if it's not a prime number, we need to check. And it turns out that there are no fast algorithms for checking. The algorithms that people know of for checking these, basically you need to try them all. And that takes a long time when n is very large. That will become another security property we use in cryptography. A couple more to finish for today. Totient of 7, it is prime. Totient of 5, 5 is prime. Totient of 35, 35, is it prime? No. So what are you going to do? You could try numbers 1 compared to 35, 2, 3, up to 34 and compare them all. But we do notice 35 has 2 prime factors of 7 and 5. And it can be easily shown that the quotient, Euler's totient, not quotient, totient of 2 prime factors multiplied together is the totient of those numbers multiplied, running out of space. Totient of 7 we know is 6. Totient of 5 is 4. The answer is 24. So we have n is 35. If we can factor it into the 2 primes, in this case 7 and 5, then it's easy to calculate, and you can check the math. It's not hard to show that the totient of 2 numbers multiplied together is the same as the totient of each number and then multiply. And since it's easy to find the totient of the 2 primes, 7 and 5 is 6 and 4, it's easy to find the totient of 7 times 5 of 35. This is a property that we'll make use of in security as well. And it will come down to how easy is it to find the totient of a number, a large number. If it's a prime number, yes, very easy, just the prime number minus 1. If the number is made up of multiplying 2 prime numbers, also very easy. In this case, it's made up from multiplying 2 prime numbers, so we can quickly find the totient. If not, it's very hard. We basically need to try all the numbers. And if we have to try a large number of numbers, it will take too long to try them. And that will be a security property we see in public key crypto. Those properties are listed here. The totient of 1 is 1. Right, that's a definition. For prime p, the totient of p is p minus 1. We saw that. And this property we just saw, the totient of n, when n is made up of multiplying 2 primes, p and q, is p minus 1 times q minus 1. We'll take advantage of that as well. Next week we'll see some further theorems that take advantage of some of these properties, and then we'll move on to public key cryptography and see an algorithm that uses these properties to make it secure.